In 1905, Einstein, with his theory of relativity, had shaken conventional concepts of time and space. To an observer, if an object is moving at almost the speed of light, namely 186,000 miles per second, time will appear to be passing more slowly. In 1913, Bohr had given a bold explanation of the relationship between light and matter. The atom, the smallest unit of all matter, emits and absorbs energy in the course of so-called quantum jumps. The quantum jump was a transition between two states which physics was quite incapable of describing. Light had been described as waves, but in 1905 Einstein had demonstrated that it also had a particle nature. These light particles were called light quanta, or photons. The same thing applied to the atom, whose components were first regarded as being solid particles of matter. But other experiments demonstrated that they could just as well be regarded as waves. How were light and matter to be understood in the face of such contradictory descriptions? In 1927, Niels Bohr compounded the experiences of physicists into an explanation of these problems. To observe atomic particles, you have to use measuring instruments. And this will have its consequences, because observation will inevitably disturb the atomic particle. What we see in reality, Bohr called a phenomenon resulting from an interaction between the measuring apparatus and the atomic particle. When in one experiment the components of the atom behave as particles of matter, and in another as waves, this is due to interactions with different kinds of measuring apparatus. Niels Bohr called this condition for our perception complementarity. Although the particle and the wave cannot be united in an overall picture, we must still accept them as equally necessary for the best possible description. The atom, as it is, free and isolated, thus lies quite beyond our capacity for perception. In 1935, Einstein presented Bohr with a final challenge. This thought experiment was only ultimately clarified many years later by the French physicist Alain Aspect. In an article which he wrote together with two other physicists, Podolsky and Rosen, in the Physical Review, Einstein posed the question, does quantum mechanics provide a complete description of physical reality? Einstein wanted to demonstrate that it was possible to perceive a part of physical reality without its being disturbed by the measuring apparatus. The experiment allowed two particles with common properties to be emitted from the same source. It should then be possible, by measuring one of these particles, to obtain knowledge about the other particle without disturbing this other particle in any way. But the real purpose of the thought experiment was to demonstrate that Bohr's atomic physics contained certain absurdities. In this same example, the consequence of quantum mechanics would be that a measurement of one particle would exercise an influence on the other. In fact, only then would the properties of the two particles be determined at all. In principle, the other particle could cross enormous distances in time and space. Bohr's atomic physics therefore implied a paradox. It conflicted entirely with Einstein's picture of the world. No event could create an effect simultaneously somewhere else in space. In Einstein's view, the different parts of the universe were only connected with each other through effects or signals that could not be transmitted faster than the speed of light, and whose origins could always be traced back to a cause in an individual part. Einstein claimed that all events have a local cause. At the Institute in Copenhagen, Einstein's article came as a great surprise to Bohr. The physicist Leon Rosenfeld was working with Bohr at the time. As soon as Bohr had heard my report of Einstein's argument, everything else was abandoned. We had to clear up such a misunderstanding at once. In great excitement, Bohr immediately started dictating to me the outline of such a reply. Very soon, however, he became hesitant. No, this won't do. We must try all over again. We must make it quite clear. So it went on for a while with growing wonder at the unexpected subtlety of the argument. Eventually he broke off with the familiar remark that he must sleep on it. The next morning he at once took up the dictation again, and I was struck by the change in the tone of the sentences. There was no trace in them of the previous day's sharp expressions of dissent. As I pointed out to him that he seemed to take a milder view of the case, he smiled. "That's a sign," he said, "that we are beginning to understand the problem." In his reply, Bohr emphasized that our ideas and concepts are rooted in our everyday experience. We are therefore incapable of forming a picture of the atomic world. Strangely enough, Bohr refrained from refuting the paradoxical consequences of quantum mechanics as described by Einstein. He believed that the two particles should be understood as a unified system. We have to do with a wholeness that is completely foreign to classical physics, he said.